All right. So my name is Zach Shvira-Conti, and I'm a research fellow here at the Alan Turing Institute in London. I would also like to introduce my colleague and co-organizer, Adria Pizzaverato, who is a visiting academic at the Turing. And for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for AI and Data Science. On a side note, if you are keen to share your work with us, please do get in touch with either Andrea or myself, and we'd be happy to find an appropriate slot. And questions may be asked towards the end of the seminar, unless, of course, our speaker for today does not mind the occasional question along the way. So without further ado, I'd like to ask my colleague, Andrea, to introduce our speaker for today. And with that, I thank you all.
Thank you, Zach. So our speaker for today is Thomas. Thomas completed his undergraduate studies in physics and mathematics at University of Houston, followed by a PhD in chemical physics from Harvard University. During his graduate studies, he worked as a machine learning research scientist at Galamon, a company focusing on enabling large language deep learning AI for mission-critical applications. After this experience, Thomas joined as principal engineer for AI, whose mission consists in developing solutions to capture unstructured data and transform it into enriched computational-ready knowledge. He's currently staff machine learning research engineer at Cash App and Twitter. His research focuses on high-performance machine intelligence systems via knowledge graphs to augment both machine perception and machine abstract reasoning. Today, Thomas is going to talk about quantum diffusion convolution kernels and graphs. Without further ado, Thomas, thank you again for joining us. The floor is yours.
Hi, thank you for having me. I'm really excited to tell you all about some of the work that I've been doing at Cash App. So how is what's going to be the rough structure of this talk? First, I'm going to tell you guys about graphs and graph data. Then I'll introduce the concept of a graph neural network. Then I'll talk a little bit about the physical principles that I see behind graphs and graph neural networks, and then how we bring quantum mechanics into the whole thing. I want to emphasize that this is the start of the story rather than the end. I have active research within my research group that is continuing this work. So if there's something that feels like it's somewhat incomplete, please do know that many of the open questions are currently being explored. As was suggested, I'm more than happy to take questions during the talk as well as at the end. Feel free to just raise your hand. And I should note, Cash App is a much cooler company than I have any right to work at. I'm using their slide templates. Hopefully, you all forgive me the cool factor. So let's talk a little bit about graphs and graph structured data. If we think about a graph, it's a mathematical structure, and a graph is a mathematical structure that allows us to encode entities and their relationships. We normally provide the entities as vertices. So these are just points, and then these are going to be connected through edges. These edges are going to represent relationships. In some graphs, these relationships might have some type of physical meaning. Maybe these are road connections between intersections. Well, in other graphs, they might be a little bit, let's say, more semantic. They might represent verb relationships, is-a connections in an ontology, for example. There is no constraint that we only have one type of edge. We could, in principle, have many types of edges, and we could have edges that are directional. The many edge restriction, or the many edge case, is referred to as the multigraph case, and the directed nature of a graph could be referred to as just a directed graph. In every type of graph, these semantics matter quite a bit. And some of the work that we are currently doing is exploring how do we extend many of these ideas to both directed multi-relational graphs. And why does directionality matter in some of these cases? Well, if we think about a payment graph, so who pays you and who you pay, it's very different to be paid $100 than it is to pay someone else $100. And so we need to be able to capture that that directionality and that money flow correctly. In addition to graphs encoding relationships through just the edges, we can also have features on the vertices, and we can have features on the edges. These features can then be aggregated together in some way to make individual decisions either about some property of the vertex itself. That might be a process like node classification or node regression. They could be used and aggregated at a graph level to do something like a graph classification or graph regression. Or they could be used in such a way to predict links between edges, so predict latent or future relationships that might exist between vertices based on the features and the graph connectivity. And what I've just outlined are some of the core problems that people try to solve in an abstract sense with graph structured data. So where do we find these graphs? Molecules are one of the most common places to find graphs. And this is partly my own bias being raised as a chemical physicist academically. When I think about graphs, I start to think about the Huckel theory and these types of 2D methods that provide actually very good chemical intuition. Here, the edges are going to be the electronic bonds. The vertices are going to be the nuclei. And we can write down what that chemical structure is going to look like. There's some nuances here that people tend to ignore. For one, molecules are actually 3D structures, not 2D structures. And for two, you have resonance structures, vibrational structures, and all sorts of weird transition state properties that are frequently ignored. But we can set all of that aside and just say graphs are frequently found in molecules. And for high throughput screening, that's a perfectly appropriate way to think about this. I additionally alluded to maps, and this is another very, very common place to find graphs in the real world. In fact, Google recently redid a significant portion of their Google Maps routing infrastructure to use graph neural networks, and were able to find fairly significant gains. And this last picture is something that's somewhat close to my heart based off of what I've been working on recently, and this has been social graphs. So this is a picture of someone's Facebook network, and you can see somewhat distinct islands of social groups. And these somewhat distinct islands might be connected by, well, so the central user there is the user, but they might be connected by some small subset of connections, but you have these distinct islands. In this, we see some of the problems that frequently exist or frequently exist within these graphs that make inference on graphs very difficult. One of which I'm highlighting here is the bottleneck that might exist between some of these islands. And we'll talk a little bit more about why that happens and how we can potentially ameliorate that in the with our method. But one of the big problems with graphs that we've struggled with is homophily and heterophily. So said simply, homophily is the problem, well, is the feature of a graph where a node's label is the same as its neighbors. So if we think about a citation network, for example, math papers tend to cite other math papers, and computer science papers tend to cite other computer science papers. You might have the odd computer science paper cite the odd math paper, or the odd computer science paper cite the odd physics, or the odd statistics paper. These tend to be interdisciplinary. But overall, you have a graph that largely the labels are going to be somewhat similar. If we instead look at a graph, maybe a payments graph, where we're trying to identify fraud versus real customers, that's going to be a highly heterophilic graph. What we mean by that is a single fraudster is probably connected to many, many customers, with very few fraudsters connected to one another individually. And so the outstanding labels in a graph neighborhood are going to be very different from a user's own label. In this setting, graph neural networks tend to struggle. And we'll explore a little bit about this in the examples that we explore. And so the question is, how can we think about improving methods to work on heterophilic data? Now let's talk a little bit about graph modeling and specifically graph neural networks. Graph modeling and actually graph convolutional networks are really quite easy. The basic idea is you might not know a huge amount about a graph from its vertex itself, or you might not know a huge amount rather about a vertex from only its own features. You might want to augment it based off of its neighbors. Why is this important? Maybe we're trying to predict something about the way that you would vote, and it's really useful to know information about who your physical neighbors are. And this comes to mind specifically because it's the 2024 election season in the US, and that's somewhat awful. And so what happens is we go ahead and we pick a vertex, and we choose to sample all of the vertices that are in its neighborhood to construct a new hidden representation. And then we do this many, many successive times. We pass through activation layers, and we pass through linear layers so that we have a learnable set of parameters that then get activated that then do the whole thing. You can think of this as specifically a generalization of a convolutional neural network that exists, that works in a non-rectangular domain. But the basic idea is that we just do successive rounds of averaging of a set of features. We can see immediately that this is going to work quite well if you're in a homophilic domain, because if you're in a homophilic domain, that means that your label distribution for your neighbors is going to be very similar to your own. We also know that your feature distribution is going to be somewhat similar to your own. And so if we're in a highly homophilic domain, then we do successive rounds of self-averaging, and then we can perform our prediction on that. In doing so, we end up with something that is quite effective. And we can see results, and I'll present some of these later, on citation networks where we actually do see that with citation networks, for example, graph convolutional networks provide basically the best in class results, especially when we take on balance the computational concerns as well. We can think about generalizing this a little bit, because we don't just have to consider these things multiplications, we could learn arbitrary functions. And so this is the general form of a message passing neural network. So we have some function that's given by psi here that goes ahead and calculates the message. This is the message for a hidden representation from vertex I to from vertex j to vertex I. We then have a transition matrix. That transition matrix can be your Laplacian. It could be your adjacency matrix. It could be the PPR matrix. There's a lot of different variants that one could explore. And then we have an aggregation function. And this aggregation function goes ahead and maps from the space of incoming messages to the space of the outgoing message with the potential for a residual connection. And this is the general structure that takes us from layer L to L+1. A graph convolutional neural network is going to be relatively simple here, because essentially all we pick up is this becomes your Laplacian, and then this becomes a averaging operator, and that's really it. So it's relatively straightforward. There's been a significant amount of work in answering the question, how can we explore techniques to alter our message passing operators? And there are just many graph neural networks out there that have tried to answer this question, but far fewer have tried to answer the question, what happens if we rewire the graph? There are some networks that have tried to do that, or there are some techniques that have tried to do this. There's the famous diffusion improves graph learning paper that provided the technique graph diffusion convolution. There's a Beltrami flow set of work that provided SDRF. And there's a couple of other significant techniques based off of these methods. But this is going to be where we choose to focus. And like I had said at the beginning, we're choosing to focus here because it's the simplest case, but we aspire to do more complex things. And so with this in hand, we can now turn to a couple of the problems that we see with GNNs. So the first is oversquashing. So basically oversquashing is the problem that for a vertex here, its receptive field damps exponentially based off of the bottlenecks that exist. So what do we mean by this? We mean specifically that you're going to have a very small influence from a vertex far on the left for a vertex far on the right, based off of the any changes in that vertex. It's not going to be very sensitive when we're doing our feature aggregation. Why is this? It's somewhat obvious to see. Here, this top left vertices representation has to get funneled all the way through this if we're doing an averaging style aggregation. That means that successive rounds of averaging are going to sort of smush everything together. We're going to lose sensitivity. And we actually see this, right? So for many cases, we see that it's incredibly challenging to have bottlenecks in graphs, and this is something that we would like to find a way to improve. We also have another problem, which is oversmoothing. So what is oversmoothing? Specifically, oversmoothing means that after enough rounds of message passing, and it sort of depends on the graph structure, you have a representation that converges to something that's the same. You can think of this as effectively thermalization, and I'll actually make this argument significantly more robust in just a little bit with a video. But basically, what people observe with GNNs is that after a small number of convolution layers, you very quickly end up with hidden representations across all vertices that have averaged to the same or close to the same value. And then we can no longer provide a good predictive method. That is incredibly challenging to figure out how to address. People have constructed all manner of message passing additions to fix this. Some have done things like add in residual connections. Some have tried to add in skip level residual connections. There's been a lot of work on this, but I will argue in just a minute that this is an inherent problem with the physical model of the GNN, and not and therefore something that we might want to think about finding ways to change the underlying physical message passing dynamics. So let's talk about the much alluded to physical models of message passing dynamics. Well, if we think about the heat equation on the graph, we have a barbell graph here. And so what I'm doing is I'm playing the heat propagation across this barbell graph. And so I'll start from the beginning again. So if we look at this, we have two sources of heat. We have heat here and we have heat here. These are in normalized units, and it's normalized time steps based off of the energy. So we're taking one, our time steps are going to be the same energy scale in both the thermal domain as well as the quantum domain, which we'll see next. So here we have temperature that is in two different spots, and we're going to watch as this propagates. So very quickly, we see that the top thermalizes. And so the top thermalizes incredibly quickly. Everybody goes to that same temperature. And then the bead that's in the middle here is going to slowly cook. And so we see physically that thermal bottleneck. And we see physically that thermal bottleneck because the temperature flux is going to be in a different direction. So the temperature flux is across the barbell, whereas the area of high conductivity is across the head of the barbell. And so it takes a long time for us to cook that bead such that we can send temperature to this other side. But slowly we're cooking it, and slowly we see that that this bead is heating up. And almost immediately as this bead heats up, the bottom of the barbell heats as well. And so we can skip forward, and then we see that essentially we have almost perfect smoothing. And then if we skip forward in time, we don't really see any actual changes. And so I'm going to argue in the next section that most modern graph neural networks undergo heat diffusion. This is not a new revolution, but I'm going to argue that we can pick a different physical model. And we can pick a different physical model like a quantum mechanical one. So what happens in the quantum mechanical one, here we have a probability distribution that has been started on this slope. And we can see very quickly that we get oscillations. So now instead of getting something that cooks very quickly and thermalizes across the top, we have an oscillating wave across the top of the barbell. We also see that we get oscillations along the backbone of the barbell, and we're able to very quickly transfer messages to the base. So that's really, really encouraging. If we move to some of the longer time dynamics, we see here that we also observe oscillations from the blinking pattern in the bottom of the barbell. And these oscillations occur both along the backbone of this barbell graph, as well as along the edge of the barbell graph. And so we can see even in the near infinite time dynamics, which is where we saw perfect thermalization of heat diffusion on the graph, we see no such thing in a quantum mechanical system. This is super encouraging because this means that we might be able to ameliorate some of those physical problems that we see with the GNN. I restarted the video. So what are the takeaways? So we see very quickly that the heat equation drives extremely quickly towards thermalization, which is qualitatively similar to oversmoothing in GNNs. We also observed that the heat equation displayed a thermal bottleneck when the heat flux and the temperature gradient vectors deviated. And this was qualitatively very, very similar to oversquashing in GNNs. By contrast, we saw that the Schrodinger's equation showed a long-lived oscillation. And these oscillations were interesting and quite robust. We also saw that the Schrodinger's equation was able to much more effectively clear bottlenecks, such that we were able to get information flow across the backbone to happen more quickly without needing to thermalize through that bead. So then where does this take us? Well, this takes us to us constructing the quantum diffusion convolution kernel. So to make some of what we had described in the previous section rigorous, we're going to talk about diffusion as convolution. So essentially, if we think about what a GNN, what a GCN is doing, specifically a graph convolutional network, well, a graph convolutional network is just taking powers of the Laplacian, as I had said. More layers of message passing is just k layers of message passing is just k powers of the Laplacian, and we're loading a parameter vector in front of it. This is just a power series expansion, Taylor expansion, or whatever. It's fine. But for a specific class of data, or specific restrictions on data, specifically that that data is going to be bounded by 1, we can show that these are going to be solutions to the heat equation. And this was actually proven in the Diffusion Improves Graph Learning paper, which is a beautiful paper. And in this work, specifically, what they were able to show was that by coming up with a resummation of different diffusion properties, we could rewire the graph to make message passing more efficient according to heat diffusion. And they were able to show that it's a cheap preprocessing method to do precisely this. So I was really strongly inspired by this paper, and I wanted to see if there was a way that I could do the same. I wanted to specifically see if there was a way that I could do the same type of cheap rewiring, and then feed in that rewiring into a transition matrix and use that with any arbitrary GNN. Because the really nice benefit here is if you can resum this into one final transition matrix, then you just feed it into any arbitrary GNN and then you're good to go. But we also just previously discussed how heat diffusion carried with it 2 very significant problems that the GNNs are known to have, which is specifically that they oversmooth and oversquash. And this warrants a question as to, can we pick a different physical model? I think that you'll all probably realize, based off of the title of the talk, that the answer is yes, we could pick a different physical model. And here, the physical model that I'm going to choose is quantum mechanics. And the reason is relatively straightforward. There are many possible physical models, anything from a Eikenol equation if we wanted to simulate like quantum optics, or not quantum, classical optics and that sort of thing, all the way to Maxwell's equation if we wanted to get kind of weird with coupling fields. But the quantum mechanics and the Schrödinger equation give us some really nice properties that I think make this somewhat easy. So we are able to maintain first order time propagation. And so it's pretty easy to import any of the first order solvers that one might want to use. We can easily use a Crank-Nicholson or something without too much issue. We still have the same Laplacian nature, so we're not picking up any fourth order tensor derivatives or anything that you might see with something like the elastic wave equation that could be quite challenging. And we have a separate potential that is tunable and engineerable going on so that we can explore that in future work. In this work, we consider the case of a free particle, and so it's actually quite easy. It's fairly similar to the heat equation. We just pick up a factor of I. And so then one might naturally ask, well, that's just the Wick transform of the heat equation. And the answer is yes, that is exactly correct. But in doing so, we pick up all of the really nice properties that that one generally gets with such a Wick transformed state. Specifically, we now have a basis of plane waves for our time eigenstates that make it very easy to calculate things like our expectation values. And I'll discuss this in just a moment. So we could do a lot of different things. We could have done time propagation and performed explicit time propagation in the way that I have described in the physical system. But I wanted to start small. I wanted to construct a method that would work with any arbitrary GNN instead of needing to construct an entire physical model. The reason that I did this, some of it was I wanted to get a small idea out there and see if it worked before I dedicated myself to a big idea. And some of it was I'm starting a research lab and I had a OKR to get at least one paper out, and this was a relatively straightforward way to get something that was probably going to work. And so with that in hand, I went ahead and wanted to compute the infinite time dynamics. And the reason that I wanted to compute the infinite time dynamics is I started to think about this as a scattering matrix. So what I was thinking about here was essentially I wanted to replace the graph Laplacian with the scattering dynamics from vertex I to vertex j when you start on vertex I at time 0 and you go to vertex j at t is equal to infinity. Thankfully, because we have the orthogonality, the L2 orthogonality of the time eigenstates, this infinite time integral becomes this very nice and easy to compute sum on this other side. Where here these phi's are just going to be the eigenstates of our Hamiltonian. Here, because our Hamiltonian is going to be just given by our Laplacian, they're going to be the eigenstates of our graph Laplacian. And then these c's are going to be the expansion coefficients into our graph Laplacian. And so we have a significant amount of latitude in how we choose our c's. And what I went ahead and did was I needed to find a way to introduce some type of learnable parameter into the system. And so this is specifically where this exponential factor comes in. So basically what this exponential factor gives is a way to, you can think of it in two different ways. Either you can think of it as we are performing a Gaussian measurement around our energy mu after we've started on with a uniform distribution of population across all of the vertices, or you can think of it as starting a coherent state on the graph that has energy equal to mu. Both are perfectly fine ways to think about this. It just depends on what exactly you push into the propagation and what exactly you push into the coherent state or into the expectation value itself. But the end result is specifically the same, and the end result is that we're able to get a transition matrix that looks a lot like the Laplacian. This transition matrix is just going to weight each one of these eigenvalues or these eigenvectors by the Gaussian weight in front of it according to some learned mu and some learned sigma. So we have these two learnable parameters, mu and sigma. Now, there are a couple of problems specifically with this. And so this is why I'm saying that this is the starting of work and not the ending of work. So the first obvious problem is here we need our eigenvalues, so E sub alpha. and we need our eigenvectors sub b. And so then the question is, how do we get around that? And the answer is we don't. So we treat this entirely spectrally. So this means that our method is not inductive, but we hope to change that. This is also computationally expensive. We make this less computationally expensive by using matrix-free algorithms, as well as the spectral folding method, so that we're able to compute subsets of the eigenvectors that we care about, rather than all of the eigenvectors. These are standard techniques in physics. I used these a lot when I was doing electronic structure theory, where I did all sorts of massive diagonalizations using techniques like Arnold iterations or log-PCG. And actually, we used log-PCG in this. But you can really think of this as a way to compute the transition from vertex I to vertex J at an infinite time. Now, because this is quantum mechanical and everything has a non-trivial probability of actually happening, we end up with something that is incredibly sparse. So if we go back to this barbell graph, we perform our diffusion and we pick up something that's incredibly dense. And this is because every possible transition is going to happen. Many possible, and actually most possible transitions are just going to happen with a near zero probability. And so then we have a sparsification step. And that sparsification step, we just have a learnable threshold that cuts everything off that is below a certain value. And so here you can see that through this rewiring, we're able to effectively learn that this node that would normally be connected to the central bead is connected to any number of these vertices in the bottom of the barbell. And the same is true in reverse. And so we not only see that we're getting a fairly reasonable improvement in our overall graph connectivity, so our rewiring is working, but it's working in exactly the ways that we'd hope to improve our overall graph dynamics.
Thomas, sorry, if I can ask a quick question. So in terms of quantum tunneling, so it can only occur when there is an edge between two nodes after the sparsification.
That's right.
Okay.
And so with what does our overall structure look like? Our overall structure is fairly straightforward. So we, a standard GNN just does k layers of Laplacian propagation. And so here we just call this Q. So we just do k layers of Q propagation. So we have a method that allows you to just swap in our quantum Laplacian. I call this the QDC matrix for the standard Laplacian and run it through basically any GNN. And I'll show you exactly how that happens and the results that we get. And you don't need to change anything else about your methods. All the math carries right through and we're all set. So we have another variant. And here, this is called the multiscale method. I call this multiscale specifically because we're able to compute at two different scales. So here we have the QDC method that is just the QDC tower. And then here we have the standard Laplacian-based propagation that's just the Laplacian tower. We feed these both into a readout function, and we learn the type of combinator that's most effective, whether that's a concatenation or a summation. Usually it's the concatenation that's better. And so we just go ahead and propagate using both, and then feed that into the readout function itself. And that turns out to be quite effective. This is especially effective in homophilic data sets. And so now I've promised experiments multiple times, so let's go through them. So the task that we're trying to deal with is node classification. So specifically, we're given a data set with the sum of the vertices classified. We use that to go ahead and learn what our readout function as well as our message passing layer should look like. We then are going to have to predict these gray vertices. And we predict these gray vertices to be either green or red. So how do we perform? Well, I just copied this big ugly table from my TMLR paper, and it's a bit antisocial, so I apologize, but I will highlight a few things. So here, if we look at the Kernel data set, we have quite a significant improvement. So the GCN results, we're looking like we're in the in the mid 40s. And adding in quantum diffusion with just a GCN gets us up to the mid 60s. If we take a cutting edge method like H2 GCN, we are in the mid 70s. And we're able to still see a fairly significant improvement. Not only are we able to see a fairly significant improvement, we also see a better, finer grained predictive performance because we're seeing a drop in the standard deviation. And this is fairly robust across the other method or across the other data sets as well. Kernel has the most significant gains of the data sets here, just because it's realistically kind of a poor test because it's so small. But we can look at other data sets. So we can look at something like Squirrel. So GCN on Squirrel, we're looking at 28, and we see a jump up to 42. Here we see a somewhat smaller jump for H2 GCN. So we're going again from 28 to 36, but not so bad. In general, so up top in the first row, we detailed the homophily. And so we see that in general for the homophilic data sets, so everything to the left, we're able to provide quite significant gains for methods like a GCN or a GAT, which are two very standard, very simple methods. And frequently we're able to make a GCN competitive with either a GAT or in some cases competitive with a H2 GCN, which is significantly more computationally complex. We have additional methods as well. So I've only discussed GCN versus QDC, but we also have two additional methods. So I compared to GDC, which is the diffusion convolution work that's from the Diffusion Improves Graph Learning paper. And here we see that generally GDC does not provide significant gains. And indeed, sometimes provides performance impairments. SDRF, which is the stochastic Ricci rewiring technique, does provide some gains in some situations, but and in the case of Sightseer and PubMed is able to achieve the best in our tables. Is frequently unable to provide significant gains in the heterophilic data sets. The final one that I've not talked about is BPDC. So the careful observer will notice that essentially what I've done is provide a bandpass filter on the Laplacian. And so then the question was, what happens if I just have a square bandpass filter? So I implemented that and did the same experiments that I did for everything else. And we see that BPDC does provide relatively significant gains, but these gains are still smaller than what we observe with QDC. So we are encouraged by the results that we're seeing here to motivate the ongoing work. Now, I should note I did this with the intention of being fair. So everything was done with 250 steps of hyperparameter tuning using Optuna. We tested were applicable on the GCN splits, and so we're averaging over 10 different dataset splits. And I'm trying to tune every possible hyperparameter that exists in any of these possible methods. So that's not letting me. Okay, there we go. So now the question is, why does this work? I had alluded specifically to it working because it was a bandpass filter, and I think that that's part of the intuition that one should have. So I went ahead and computed the homophily of these data sets as a function of our spectrum. And I found that the homophily was highly spectrally dependent. So if we look at a data set like Chameleon, we see a high homophily at minus 0.5. And for a data set like Actor, we see a high homophilic peak between 0.2 and 0.5. Some of these data sets like Quora, CiteZero, and PubMed, which are all going to be citation networks, have homophilic peaks that exist in some parts of the spectrum, and we'll see that that we're able to pick those up. But overall are actually remarkably smooth. So we'll compare these spectra in just a moment to specifically the spectra that we were able to recover. So let's take this Chameleon peak that exists just above 0.5. If we look here, our Chameleon peak that we're able to find for the single QDC bit, it has a very, very large cluster at just above 0.5. So what are we looking at here? We're looking at the hyperparameter plots for mu and sigma. So sigma is our standard deviation. Mu is going to be our mean. This left-hand side is going to be the predictive accuracy. And then this bottom is going to be the eigenspectrum index. And so we see a very, very large cluster at this minus 0.5 eigenvalue, which is exactly what we expected to see based off of this large cluster here. If we take something like Actor, we see a large clustering between 0.5 and 1, which is a little strange because we don't see it showing up there. But then if we look at Squirrel, we see the same peaking in the center that we would hope to see. In general, for something like PubMed, where we see we see that we're trying to pick up some of those higher frequency spectra as well. That higher frequency corresponds, we believe, with trying to pick up some of this information on the right side of that central peak. We also observe that there are long, flat basins for sigma. So we believe that sigma is not as valuable of a hyperparameter as our mu specifically is. And this sort of makes sense. If we think about the way in which our hyperparameter tuning is happening and the way in which a Gaussian works, you're going to have a lot of flexibility in the way that you pick your tail. So there's some additional questions around the how our model is working with respect to the hyperparameters that have been chosen. I went ahead and constructed a violin plot to show that there are broad populations of results that outperform the baselines. So here, yellow is going to be the GCN, blue is going to be the GCN plus QDC, and then the green is going to be the multiscale variant. And here we observe for squirrel, for example, the GCN is entirely contained within this lower chunk. And then we have the majority of our model population significantly above that. The same is true for chameleon, Wisconsin, Texas, and even Cornell. And so I'm pretty comfortable saying that in the heterophilic cases, we do quite well. In the homophilic cases, the story is a little bit more complex. And that's largely because in the homophilic cases, these are simple and well-solved data sets by GCNs already. So what are our conclusions? So the first is you can read the full paper in the Transactions of Machine Learning. It was accepted with all of the revisions done a few weeks ago. And there's the link. And I'll share out these slides. So I've argued for a physical perspective on over-squashing and over-smoothing. And I hope that this has been something that you are at least interested or at least curious about. I presented a rewiring methodology that uses a different physical formulation. And I'm going to use that as a basis for ongoing and future research. We validated this physical perspective through extensive experimentation, and we're able to show lifts across the board. Now, one limitation that I spoke about is it's an explicitly spectral method. It's computationally expensive, and that there's no getting around it. I'm hoping that this is a way to prove out the idea rather than suggest that it's something that everybody should drop and move to tomorrow. But I'm hoping that we can use it to learn more about different physical models. And finally, I'm hiring to work on projects just like this. If you're looking for an internship or something similar, even early career research scientist roles, please reach out. I run a research lab. We focus on publishing, and this paper and all of this work was supported implicitly by Cash App without any reservations. So if this is the type of work that you want to do, it has a home in corporate research labs, and we're more than happy to find a way to make that work. So please reach out. My email's there. And with that, I will close for questions or comments.
Thank you very, very much, Thomas. That was extremely interesting. There is one question that came in from Nashiketa. Shall I ask it on your behalf? Okay, I will go ahead and phrase the question. So it's then the message passing is statistical. Would this lead to missing information? This was earlier in your presentation.
So the message passing is deterministic in the way that I had formulated it initially. But so if we go back here, in the way that I've formulated it, it is deterministic. That being said, there is going to be missing information in a few different ways. So the first is through the oversquashing property. So information is going to be missed just because you end up bottlenecking information that you're trying to transfer. The second way in which it's going to be missed is if you are exploring any possible scaling methods. So something like graph stage, where you are statistically sampling your transition matrix, you're going to miss information as well. And that's going to be problematic. In the case of the way that I rewired the graph, you're also going to miss information. And that's because we are removing some edges and adding others. And so if we go back here to this bit, we see that we are going to be adding additional edges. When we add additional edges, we are alleviating the bottleneck, but we're also going to be adding in additional things that need to be averaged over. That has the benefit of reducing the potential over squashing problem that could make the over smoothing problem worse, depending on the distribution of features. And so it's always a somewhat tricky balance. And I believe that this is why, if we look at the way the final performance metrics, I believe that this is why QDC plus H2 GCN generally performs better than the GCN method itself.
Thank you very much. I hope that answers your question. So do we have any other questions? We have a question, or a comment rather. Oh, it was a question from A. Margolis. It says, great talk. Have you looked at performance on chips specifically designed for GNNs, such as IPUs or other techniques for optimizing the use of GPUs?
No. I would love to. Hold on, I'm just writing a note.
Oh, no worries.
Yeah, so I would love to. The issue that we ran into is just I can't get access to GraphCore type chips. So that's been a little bit more challenging. But that is something that would be super, super exciting to explore. And I just wrote a note to circle back and see if there's been any movement on that, because I would love to explore that. My PhD, I did a huge amount of high performance computing. And so I get unreasonably excited about those types of architectures.
Thank you. He also made the comment, PyTorch 2.0 in particular tries to optimize GPU use.
Okay.
Right. It's 2 o'clock. I really have to run, but I do have one quick question.
Yep.
I was wondering with regards to the rewiring aspect, whether you do encode, whether there's like any capacity or scope to encode geometric knowledge about, rather knowledge about the structure of the physical system that you're kind of trying to model. Because I could see how maybe working in lower, more fundamental spaces could potentially alleviate from the computation expense. But this is, of course, very specific to the physical system. I don't know much about quantum mechanics, but I'm talking about sort of differential geometry.
Yeah, so that's a really great question. And one that we're starting to try and explore through properties like our potential tuning and potential engineering. But we're still in very, very early days of that type of work. I would, if you're interested, we can chat offline about that in more detail. I think that it would be really, really cool to learn a little bit more about what you had pictured with that.
Thank you. Yeah, sure. I'll reach out. I'm very much fascinated by that. So okay. I am conscious of the time. I thank you so much, Thomas, for, unless there is any burning question, of course. But in the meantime, I'll thank you, Thomas, for joining us today and for sharing your work. And yeah, I look forward to seeing you all again for the next seminar. Until then, have a great day, everyone, and thank you.